When stars collapse, they can leave behind incredibly dense yet relatively small and cold remnants called neutron stars. If two stars collapse in close proximity, the remaining binary neutron stars spiral inward and eventually collide, with the interface where the two stars begin to merge heating up tremendously. New simulations of these events show that hot neutrinos, tiny, nearly massless particles that rarely interact with other matter formed during the collision, can briefly get trapped at these interfaces and remain out of equilibrium with the cold cores of the merging stars for about 2 to 3 milliseconds. During this time, the simulations indicate that neutrinos can weakly interact with the star's matter, helping to push particles back towards equilibrium and providing new insights into the physics of these powerful events. A paper describing the simulations, led by a team of researchers at Penn State, was published in Physical Reviews Letters. The growing interest in binary neutron star astrophysics stems from the fact that there is no way to experimentally recreate these events in a laboratory. Making simulations based on the mathematics of Einstein's general theory of relativity are best window into understanding what happens during a binary neutron star merger. Neutron stars get their name because they are thought to be composed almost entirely of neutrons, uncharged particles that, along with positively charged protons and negatively charged electrons, make up atoms. Their incredible density, only black holes are smaller and denser, is thought to compress protons and electrons together, turning them into neutrons. Neutron stars get their name because they are thought to be composed almost entirely of neutrons, uncharged particles that, along with positively charged protons and negatively charged electrons, make up atoms. Their incredible density, only black holes are smaller and denser, is thought to compress protons and electrons together, turning them into neutrons. Neutron stars are effectively cold before merging, despite potentially being billions of degrees Kelvin, because their incredible density means this heat contributes very little to the system's energy, said David Rodicha, assistant professor of physics, astronomy, and astrophysics at Penn State's Eberly College of Science and leader of the research team. When they collide, they can really heat up. The interface of the colliding stars can reach trillions of degrees Kelvin. However, they are so dense that photons can't escape to dissipate the heat. Instead, we think they cool by emitting neutrinos. According to researchers, neutrinos are formed during the collision when neutrons in the stars crash into each other and break down into protons, electrons, and neutrinos. What happens in the first moments after a collision has been an open question in astrophysics. To address this question, the research team created simulations modeling the merger of binary neutron stars and all the associated physics, requiring vast amounts of computational power. For the first time, these simulations showed that neutrinos could indeed get trapped by the heat and density of the merger, albeit briefly. Hot neutrinos remain out of equilibrium with the star's still cold cores and can interact with the star's matter. These extreme events push the boundaries of our understanding of physics, and studying them allows us to learn new things, said Rodicha. The time during which the merging stars are out of equilibrium is only 2 to 3 milliseconds, but in this context, time is relative. The orbital period of the two stars before merging can be as short as 1 millisecond. This brief out-of-equilibrium phase is when the most interesting physics occurs. Once the system returns to equilibrium, the physics is better understood. Researchers explained that the exact physical interactions occurring during the merger could affect the types of signals from binary star mergers that could be observed on Earth. The next generation of gravitational wave detectors could be designed to look for such signal differences. In this way, these simulations play a crucial role in informing future experiments and observations while providing insights into these extreme events in a sort of feedback loop.